Da 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 da. Da 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 da. Da 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 da.
Here, at Rötz 4.0 World Headquarters, development has been proceeding, forming the apex of fastidious engineering and overly ambitious additive manufacturing. Unofficially crowned the fastest FDM printer in existence, the Minuteman machine achieves mind-boggling speeds that defy both logic and budget constraints. The Minuteman is a triumph of global collaboration, powered by motors from nanotech, celebrated for their hypersynchronous torque realignment. The extrusion system fuses quadruple filament harmonization by Bontech and thermoflux dynamics from Slice Engineering. The impossible has become reality thanks to the sponsorship of PCB Way and project supervision by the engineers at Rötz 4.0. Their dedication to unnecessarily complicated machinery, as well as video intros, knows no bounds. At its core lies the granite-integrated air suspension print bed, gliding on a pneumatically balanced cushion to virtually eliminate side fumbling. This allows us to achieve a layer accuracy only theoretical mathematicians could hope to measure. The multi-filament synthomelt hot end assembly is a masterpiece of helicoidal thermal coalescence geometry. By harmonizing 4 filament strands, it achieves extrusion speeds exceeding 350 cubic millimeters per second, a rate previously reserved for hypothetical scenarios in fluid dynamics textbooks. Driving the Minuteman is a winch kinematic drive system where open-loop stepper motors, selected for their thrilling indifference to feedback, elegantly maneuver the print platform via girdle-reluctant cables. These are anchored on a granite foundation to prevent anything resembling instability. Weighing in at a modest 1,300 kilograms, the Minuteman's aerospace-grade granite construction ensures unparalleled dimensional stability. Some would call it overkill. We call it gravitonic equilibrium engineering. Of course, every system is paired with state-of-the-art electronics, featuring quantum-adjacent signal pathways and a unique ability to suppress harmonic resonance drift. In summary, the Minuteman is not just a printer, it's a statement. With unrivaled speed, side fumbling negation, and a weight class typically reserved for forklifts, it obliterates the boundaries of conventional manufacturing. Because when you're the fastest, you don't just print. You redefine the very concept of time itself.
Hello, ladies and gentlemen. Welcome to the 10th and final episode of this season on the Minuteman machine. Our ultimate goal is to 3D print a Benchy in less than a minute. On this episode, you follow me on an epic journey where I try to get a handle on all the unique solutions that are in this machine and try to break the world record. And we're going to start by putting on these parts I got sent over by PCB Way. So before we do anything, we have to address the mechanical situation in here. All of this is working pretty damn fine, but I got a problem with temperature. These are printed in a carbon fiber reinforced material and they held up pretty good in terms of temperature, but as with all these kind of plastics, they tend to wander if they're near their glass transition temperature, and that has been the case with these motors. Even if they just run at 60-70 degrees or something, you get a very good heat transfer from the aluminum housing as well as the metal shaft, and that's like transitioning into these printed parts. So what I need for this setup to run is to have these cables under a constant tension, which was quite a pain to get dialed in. As soon as anything of this moves, the whole system collapsed basically. If I got these motor temps just a bit too high and these materials soften just a bit, there will be some slack in the line and it won't work. So that's why, let me head over to the desk. We got these parts in the mail. And as you can hear, these motor mounts have been SLM printed in solid aluminum, and these pulleys have been polyjet printed in solid nylon. And just for comparison's sake, this is the old one without any screws. It's at 29 grams, and this one is about 13 grams. So less than half of the weight we got in here. So let's put that on the machine, get everything hooked up, and then we'll do a proper review of these parts. Also, while we're at it, we had that strange squeaking noise in the last episode. I can't really figure that out, but as you can hear, this has the slightest bit of a bow into it, and all those pads aren't really touching the plate. So I'm gonna relap those, also these pieces, and make that air gap a lot smaller. This used to be somewhere in the 40 to 50 microns, but we're gonna do that a bit closer since we do now have the air system hooked up, etc. So let me lap those, put them back on the machine. Well, would you have a look at that? So it pretty clearly is the upper side. And I don't really know what's going on, but I will find out. This is again a very strange side quest we're on. Because just follow me. So the first thing I checked was if this here is touching at some random points, but it isn't. As you can see, there is a gap of light as well as here. I made sure that this is below that surface and filed some down. So I think what happens here, that's at least my theory, I should have left that bracing in there. It was like another 5 grams saving, and apparently it just starts to vibrate if it's been excited in that direction, and this is somehow resonating, and when it's here it doesn't do that, and that's exactly what we have seen on the machine. It has just been one direction. I think for now we're gonna switch this up at some point anyways. Let's just go with it. I don't think there's too much we could do about it. So I do the lapping job in terms of getting the height accurate, and then we'll just put it on the machine, and we just have to live with that situation. This is the measurement, so it's just shy of 20 millimeters. It's 0.85, 0.85, 0.85, 0.84 maybe, and then these standoff pieces, pretty much 85, 85, and a few microns under that. So basically there will be no gap. The air is gonna create that gap by itself. And yeah, let's see how bad we made the squeaking. Alright, we're just a few minutes into the video, but let me address something real quick. So, as I said, this video is being sponsored by PCBWay. And while you haven't seen a real sponsor on this series, I'm glad I did it, because this is the reason why projects like these are possible. So have a look. When they approached me, I said I have no intentions on just giving out some kind of a message. It's just gonna happen if the quality is right. And I'm at a point where I can give you my full honest review on these parts. Have a look at those SLM printed aluminum parts. So I just had to run a tap through the M4 and M3 screws, and since I modeled those in here, this worked out just perfect because the tap isn't wandering off or something. Well, and both of these parts, and especially the nylon polyjetted one, is just sublime in its quality. Well, you basically don't have any runout on this. It seems to be really, really strong compared to what I got on here before, cutting down the weight in half. The threads run butter smooth, and all the fittings on like the metal shaft are really precise, so I didn't add any tolerance, it just fitted. In terms of experience on the website, I just got on there, uploaded my files, and got an instant quote basically on the parts. What kind of surprised me is that a few minutes later, apparently an engineer contacted me. He was asking about a few wall thicknesses, if we can change them, and also we talked about what kind of material we should be using. First, I was into PEK FDM 3D printing because it has way higher temperature resistance. Then he tried to talk me into also doing it in aluminum, but just because this is purely weight reduction or inertia reduction, we finally settled on this polyjetted nylon material. If we turn it on in a few minutes and really give it the beans and they break or something like that, it's purely my fault because I'm the engineer who designed this stuff, and if I run it out of their specs, well, it's my fault. Manufacturing-wise, these are sublime. So let me finish that and let's see that we can get movement on the machine. So you meet me at a lovely Sunday here in the company, and as you can see, all these parts are put on the machine, and I also got the accelerometer hooked up. And now we're going to do some input shaping. And I think if you're here watching this video, you might eventually know what input shaping is, but let me give you a very short example of how that works. Let's say we want our printer to follow this code. It does a 90-degree sharp corner in here. The G-code basically just defines take this point, go to this point, and then move here with some kind of a speed, which is the SCV, the sharp corner velocity defined in Clipper. But since we're not living in a fairy tale, what ends up happening in this imperfect world is that our printer is basically gonna go something like this. It will overshoot its target because of elasticity and so on, and then it will swing back from the stored energy in this system and eventually gonna go on this path here. And this effect is what you can see as ringing in your 3D printed structures. So to get rid of that unwanted movement here, there are a few options in terms of cancellation. So in very sophisticated CNC machinery, etc., there are active sensors that actually read data from an accelerometer and see how much this is away from the perfect line and actively countersteer that movement right here when it happens. Clipper, however, does this sort of in a different manner. Let's call it a passive way. What we ends up doing is exciting our motion platform with all sorts of frequencies, then measure its response on that, find out where its resonant frequencies are. And by doing that, we can select various kind of filters that we put on top of our, in this case, pencil-lined optimal G-code. And what Clipper will do is actually change the G-code to something that looks like this. So it will just start this turn earlier on and cancel out this overswinging here, and then it's gonna cancel out this spring back force that is coming the opposite way of our optimal curve. And this is what we're going to do on the machine now. This accelerometer is being installed here right on the motion platform, and we're using the Clipper intern routine to excite this moving platform in frequencies from around 10 to 115 Hertz. And then we're going to see what the results are and have actually Clipper determine what is the best filter for this application. And I did some preparation and troubleshooting beforehand so we can get straight into action. I gotta admit, it's the very first time I'm actually setting up an input shaping on Clipper software, so bear with me. I'm still in the learning curve as well. This is the very first measurement you're seeing here for the x-axis and the y-axis. And I still don't really know what that means. We have to play around with a little bit, and I think this system is somewhat very unusual in its behavior. In all the documentation, I have never seen a peak somewhere here in the, 5 to 10 Hertz region. We can see we have another peak down here at the, let's call it 40 Hertz line, but then it smooths out, and all the peaks I've seen so far in documentation are somewhere in the 50 to 100 Hertz region and spike up pretty violent here. So we'll see what that means. These measurements were done with these standard settings, which is like using accelerations just up to 10K. We know we have to go way, way higher than that. And we're going to rerun these tests now. I'm going to get the camera set up for you, plug in a lot higher numbers. So we see accelerations of somewhere in the range of 250K acceleration. I've still got motors turned way down, but to get closer to the final accelerations we're going to use in our printing moves. All right, the following measurement is in X direction, and we're gonna see accelerations of 1,000 millimeters per second squared per hertz. That was way more violent than I anticipated it to be. We're gonna rerun the same test in the Y direction, and I'm gonna show you some pretty weird resonances I can see in the rest of the motion system, with the cables especially. So we're at 90 and see what this cable starts to do. Starts to resonate real bad. And now we're gonna have a look at here. This is at 100. Okay, so we're looking at the graphs from the test you just saw, and it is clearly visible that all these power spectral density, whatever that value exactly means, is going way up. So let's have a look at the ZV shaper, which is giving me an acceleration up to 50K to use. That is this dotted line in blue up here. And this is basically the cancellation Clipper wants to lay over the actual G-code. And as you can see, this is in a pretty high region, about 115 Hertz. And this turquoise line is basically what Clipper expects the amplitude to be after putting in the cancellation. So I think a lot of this stuff here is due to the cable swinging so with such high amplitude. I'm gonna rerun the tests just like we did before, but I just have these like pliers sitting here, and basically once this starts to resonate, these hopefully will dampen out all those vibrations, because if this vibrates, and I know that these strings won't stretch too much, we have to account for the length somewhere in the system, and it's gonna excite this motion platform big time. So let's see if we can just mechanically get rid of resonances before we actually do apply any kind of software filter to it. 90. Alright, looking at my screen, the left one is the previous attempt, and this is with the pliers in the way of the cables. So we're basically cutting the free length of that cable in half and therefore reducing its resonant frequency. But as you can see, the amplitude even got higher, and the applied shaper is also correcting even more in a higher region. I want to test this again and have placed loads and loads of items in the path, effectively shortening the free cable length even further. There's this stuff in the back, there is some motors standing here, so let's rerun that. It appears to having the resonant frequency of the cables lowered doesn't really affect it to any good measure. The first one with just hanging free air, what I can read out of these graphs, the best result. There are many things we could do now about the system, testing different resonance frequencies, etc., and just play around with the mechanics. But most of this will get changed up anyways. So let me apply the recombinant shaper that Clipper has given me for these kinds of accelerations and actually rerun the tests with these applied. I don't know if they do apply when you trigger a measurement. Let's see. $100. So apparently Clipper doesn't include its own shaping into its measurements. I guess that makes sense. But I was hoping to see the real effects when it does apply its own cancellation over its measurement. Let's see, this is just a shot in the dark. There are so many things we could do different and test, etc. But I just want to know as a baseline. This is the just sub 10 minutes Benchy we printed last time. And I have this exact G-code still on the firmware. We're gonna run just that with the shapers applied and see what kind of a difference it makes. That didn't work out. So this is the back part of the latest design iteration I did on the nozzle sock. It basically, there is a front and a back half of it, and it's completely surrounding that nozzle down there. I think it's kind of flimsy anyway for a part printed in such a brittle material. In the future we're gonna have this 3D printed in ceramics, but I need to go through a lot more of iterations before I can send these pieces off. So these are the two Benchies in comparison. This is the earlier attempt, this is 15 and this is 16. And what we're looking at is the effect the input shaping has got on the model. We're not looking at extrusion, etc. There's a lot of stuff to be done, but we can say that those resonance up here, you can see it best, has been not eliminated, but there are a lot less. Promising looking feature is the chimney. Have a look at how these differ. This is basically a circle. This is something like a star shape. So this is a verification of me having set it up properly. We could argue about these measurements. The measurements done by Clipper were at a lower acceleration than this print has been. So the next thing we're going to do is to set up pressure advance. and see how good we can get that extrusion, because obviously there are a lot of things to talk about. The cooling situation is one of my main issues right now. I can't really give it the beans because the part, also the second one, the heat sock did break, and the whole nozzle situation is being blown by really cold air from the back, so that doesn't make any sense. And also, if you're setting up a printer and you're doing all of these calibrations, it is a smart way to do the input shaping before you do the pressure advance, because input shaping is going to influence the readings on the pressure advance. Clipper is going to actually alter the way we follow that ideal curve, or sharp corner in this example, and therefore we have to do a pressure advance tuning after we have this altered path in our G-code. So just very short, what is pressure advance? Let's have a look at this graph, this being the time and this being the flow. Let's say we need this much of an extrusion during a normal G-code move. And what ends up happening is if your controller just follows that G-code move, it's going to start here, it's going to slowly build up, and then it's going to extrude some more material in here, and then fall off here again. So basically the real amount of extrusion that is exiting the nozzle is kind of shifted because it takes some time to build up pressure, and also plastic has a certain amount of elasticity, so once you take the pressure back, it won't fall off again because there is still expansion after you took off your pressure from above. So again, what Clipper is doing, it is calculating something like this. So by starting this extrusion move more rapidly than requested is that we build up pressure inside the nozzle really fast and at the expected rate. And then we do our extrusion move here and drop off the pressure inside the hot end before we reach our endpoint, because there is still material oozing out at a very fast pace, especially with this kind of hot end. And then it's going to taper down to meet at this point here. This is the result of the temperature tower. So I think there isn't too much of a difference here. They all look kind of terrible, but my prediction is the following. This hot end is not comparable with anything else on the market, because you get so much volume inside your melt channels that this will make a huge difference. And maybe we're looking at something real absurd like this here. But see, in a G-code move, there is XY movement, let's say from this point to this bridging point. And also it contains the information about extrusion. So if you deposit your material here and have a connection to that bridging point and then just going to pull that string across, it's going to land here. But if your move already starts going but your pressure isn't really there, the material starts to leak out of the nozzle once you're in free air. And all of that material is then being washed away at this corner it is hitting. So, and I guess that's why we don't see any difference in the temperatures here. They look all equally bad. But yeah, let us see if we can print a real pressure advance test and then repeat this. Make this kind of iterative, go back and forth to find the sweet spot of pressure advance and temperatures, and then gonna print the same Benchy again. Like we have 3 versions. One of them is plain, one is with input shaping, and one is with input shaping and pressure advance. It's the next day, and when I say we do have Julian on board as well. And we're doing the pressure advance testing. This is the Orca slicer included test. It's going to actually increase the pressure advance value each layer. This has been set way too coarse because I have no idea if that hot end I built is basically in the realm of a direct drive extruder or if it's a Bowden setup. So we ran something that is pretty coarse in terms of these values. And I think we should be somewhere in the 0.5 range. And now we're going to do a fine resolution run and see if we can narrow that number down. So it's a couple of days later. I don't know how much of the footage you saw when Julian joined me overnight. Thing is, if I got someone here that is helping me and does have a very good opinion on this machine, I'm not very eager to film too much of it and just use the time, because actually filming takes up a lot of time in terms of progress rates, etc. Let me try to summarize what happened this evening. So first of all, we tried to do some pressure advance testing. The results were, let's say, a bit of inconsistent, and I wasn't really sure if these results are due to moisture in the filament or what was actually causing this. We got a number for pressure advance in the system. We did 0.2 as a value. I have no idea if that makes any sense, but we also tried some different filament in here for like reprinted those temperature towers, etc. And the problems we identified as moisture in the filament kept on persisting, and this was right out of the vacuum seal. And then we moved on and sliced a Benchy, which was just shy of 2 minutes, with the plan of actually running it at 20% speed override, then at 40%, 60%, so on, to get down the numbers and not start at a 2-minute run. But yeah, actually I messed up and we went for a 100% run, and this is the result of it. It's this cute little thing, and it did actually, right at the chimney part, I had some error again because of cooling. Well, yeah, and at some point we have to decide what is actually a Benchy and what is not. Well, you could argue you recognize the Benchy down there. I wouldn't dare to post this as a record if it would be one. Well, yeah, and then it was already almost 1 in the morning. We decided to do one last run and do a video of it. The only things we changed is the orientation. I think it was like this on the build platform. We changed it to this orientation, and we got the temperatures 10% down. And let's play that tape and then compare the two we got. Okay, drück auf Go. Jetzt. As you can see, this is still far away from perfect, but it is an order of magnitude better than this one. What I want to show here is the progression we can make with the smallest of adjustments. This is the 17th print this machine has ever done. And I can't emphasize enough how much of a challenge this is to identify the problems we're having on here, because let's say you want to build a sub 2 minute printer. What you basically would do is to go for the highest flow rate extruder on the market. You have your ballpark pressure advance numbers, you know how to run them. In terms of your motion system, you're either gonna use some Cartesian machine or a Core XY. Those are basically the two options you got as of right now. And yeah, you got some numbers on where are like typical resonant frequencies on these systems. What kinds of numbers do I have to extract from input shaper measurements? You know what motors to use, you know pulleys, you know belts, because this is all a worked out system. These systems literally have millions, if not billions of hours on them, and you benefit from all the improvements the community has done on them. And all the information are rarely available for you on whatever, in slicing, development, etc. Basically, you have all of this. And if you have a look at here, different motors, different drivers, different kinematics, different code, etc. And my job is to identify what's going on in this system. Where are these problems located? Is this extrusion here not at the right place being a thing of the motion system actually not following the planned path? Or is it too much or too high of a temperature extrusion? Or is it low on cooling? Is it high on cooling? Whatsoever, you name it. What I will do now, I'm gonna change the cooling situation. This is like the third iteration of a cooling sock I put on here, and all of those broke. I was aware that this material is kind of brittle, and I want to go ahead and have these printed in ceramics, but those will arrive next year. So I have one of these left to put on here. Hopefully these will shield those heaters off enough so we won't trigger those values. And then we're going to go ahead and do a slightly updated version of this cooling situation, because these needles are really close to the nozzle, and I want to see if that makes a big difference to actually have a bit more cooling on the part. And I'm going to chop off another set of these valves here, like 10 millimeters away from the heating block, so we have more cooling on the part itself and not just on the extrusion, because I think the extrusion is being blown cold and I have no real idea about the extrusion temperatures right after the material exits the nozzle. In terms of slicing, I sliced up a 2-minute 15 Benchy with some luxury material to make it a bit more quality-ish. And also the accelerations are at 350K, so I think we can run these just back to back without getting everything heated up too much. And I just want to switch up small little things and see what the results are, and also write that down. So let me plug everything in and let's run another run here. I put in the last of these socks, and we're gonna run 3 or 4 times the same G-code. First one will be with the cooling pressure turned way down. The second one with everything I got. Third and maybe fourth test is this guy. We'll set something like this, and then we'll start with whatever was best in the first 2 scenarios. I've been troubleshooting for the better part of a day here, and I found out so much stuff, so let's talk about it. You saw extruders 1 and 2 move kind of in a shaky motion, and extruders 3 and 4 kind of in a very fluent motion. And I've been chasing my tail again. So extruder 1 and 2 are hooked up to one driver, and 3 and 4 are connected to one driver. So long story short, I use my standard extruder setup, and then I connected or synced another driver on the main board to do exactly the same thing as this does. And this has worked flawlessly until now. And then it started to develop that problem, and I kept going back and forth, and apparently the pressure advance values we put in there are only applied on the first set of extruders. So the linked one doesn't get the pressure advance. And while we may fix that with some coding, etc., I don't want to look into that because I have a working solution for right now. And that is to have those hooked up to, like, on the main board there's X and Y in your standard configuration, and Z has a double outlet for steppers, and I just plugged all 4 into those 2 ports. And that does work because I can run them at 0.5 amps or something per motor, and this will be plenty for the application right now. Let's say for a sub 2 minute Benchy we need somewhere around 150 cubes of filament flow, and that is no problem in this setup. So we're gonna leave it as is. Then with those things figured out, I did some new pressure advance testing blocks. Have a look at those last few millimeters. This is exactly what I wanted to see. This basically comes down to temperature. I guess what we need for this kind of a setup is some kind of a table that sets the temperature depending on the flow rates. That's what I was talking about in the video before. This is capable of melting a lot of material, but if it stays in there for too long, it will degrade. And this is exactly what you can see here. The longer the print takes, the more of imperfections are getting in there. And as soon as I started pulling temperatures down and down and down, it found a sweet spot very fast. And I tried to extrapolate that for our next Benchy. We can go right back to the testings we would like to have done in the first place. And also one very interesting thing is the cooling seems to be a lot higher on one side than the other. And I found out that this was also happening here on the pressure advance test. And I found out that just the slightest adjustment was off, and the most outer needles were just hitting the block and not the filament, but this side was, and it was like in this orientation with this side being bad. And after I just turned it a few degrees, it was optimal on both sides. Our test number 19, as I said, adjusted the air nozzles. I'm going to turn pressure advance off to get rid of further variables, and I hope we fixed the extrusion for now with this, and we're going with 210 on the hot end. That was number 19 with very, very low amounts of cooling. It was basically just on. Let's run that same test with mediocre cooling settings. Number 20, with mediocre settings, already a lot better. Let's go all I got on cooling. See if it will stick to the plate. Low, mediocre, high settings. So I think this is getting somewhere. It still is a 2-minute 10 Benchy. At the end you saw something break. That was again one of these tensioners. Let me fix that, and then we're gonna put on the other cooling element, which is like focusing a wider area, and rerun these 3 tests and see what we can conclude out of them. This is the comparison from the old cooling fan duct to the new one at mediocre settings. They basically look pretty much the same, I guess. So let's do the high flow test. Another thing, this one has at least a chimney-ish object attached to it. Put that on the scale here. It says 9.43. It is estimated to have 938, so no sign of under extrusion here. All the material that should be here is here. So I guess we can go even lower with the temperatures and suck out more of the heat. Let's do high flow testing. Again, old duct, new duct. This encountered a serious delamination from the build plate. So the front area seems to be of the highest problem, but other than that, I think we're slowly getting in the realm where we can say this is a Benchy. Let me think about what we're doing next. Well, so the next move may seem a bit rednecky, but let's see if blowing additional cold air to like the side that is improper cooled, let's see if that does anything. And I know, this isn't being wrapped in some kind of a heat material, so yeah, the most outer channel will be blown cold the most, but yeah, let's see. Yeah, that didn't work out. 23 and 24. So, but one thing I did notice. The fan was blowing hard on the nozzle and eventually you could see it was too cold. Let's just assume for a second that all of our problems here are not being too warm of a filament. Maybe the stream of air here is when this Benchy passes by, it gets somehow directed upward or something and blows the nozzle cold. So how about that for a theory? The test I came up with is let's just turn it sideways, 90 degrees, because the layers facing west and east are looking okayish, while north and south are not. Let's turn it 90 degrees and see what happens. So it was like this on the build plate. There's a substantial amount of that back part missing, but also I just saw in the slicer that this is, I didn't have seams on random mode, it was all located here at a starting point and then moving around like this. Next test, same orientation. I pulled some speed out of the inner and outer walls. We're now running both of them at 1250 to give it a fighting chance of depositing the material here. And then I changed the seam going diagonally up here, so facing the stream of air. Let's rerun that. Print 26. Now have a look at that. So I guess now we're sailing in the right direction. For print 27 I upgraded a few things. I faced it like northeast to have that full air blow here on the seam line. I changed up some infill settings, gave it a bit more anchoring point because the infill is pretty much lining up with this seam and I hope that it has more of a chance to catch there. I pulled another 250 millimeters from the both walls. They're now at 1 meter a second. And I took down some time at the chimney part. So let's rerun that. Shoo shoo! Now that's progress. So Test 28 will be some updated infill code and 5 degrees less on the nozzle, now at 215. I'm in the preparing for the sub 2 minute run, and I think you can see my screen now. So this is what I came up with. Let me get rid of that priming object here, and we're gonna end up with a flat 2 minute Benchy. In my experience, it tends to be a second to 1.5 faster in real speed than is being calculated. So that should bring us to 159. This is my speed tab, first layer, babying it, 250 to 500 millimeters a second. This is our printing speed, outer wall, 1000, inner wall, 1250, and then somewhere between 1500 and 1750 for all the insides. I did some slowdown for overhangs, which seem to be helping a lot. Travel moves are at 2 meters, and then there's our acceleration tab. Well, I don't want to sound smudge, but let's put in some mediocre accelerations in here. We could go a lot higher, I guess, but I'm really pushing it in terms of I've been running these back to back. Nothing overheated, nothing broke. I just got the feeling that something's breaking in a couple of seconds. So I don't want to push it too far. I pulled up the motors to 2.5 amps. We were running 1.5 like all the time before. Coming down to this section, this is a square corner velocity of 30 millimeters a second. Here you can see a plot of the speeds throughout the print. And this is the flow. The red being at a 150 cubes, outer wall somewhere between 90 and 100. We're going for 210 degrees on a PLA, which is pretty low, but again, I don't want to lowball, but this is not nearly maxing out this hot end, and we simply don't need that high of a temperature because otherwise it's just gonna be all like liquid when it comes out, and we don't want that. So with these kind of speeds, maybe we up this to 215 because latest tests were at 210 and that worked out the best of all. Maybe with those added speed we are going back to 215, but that's it. We don't need any more. It gets worse from there. So what I'm going to do now is set up a few cameras and then hit go at some point and hope for the best. Yes! Woo! There you have it. To my best knowledge, I just tied Monica McWoof's 1:59 world record. And you can be the judge on which is the better looking. In my opinion, it's hers. I was kind of surprised. So from the 29th to this print, this is the 30th, the only difference is 100 something K in accelerations. And I thought, well, I have this pretty much dialed in at 2 minutes 10. I'm just going to plug in different acceleration values and then we're good to go. But yeah, for a result, and with this amount of seat time on the machine, I'm really, really happy with how that turns out. In a few of those components, we have so much headroom left. And in a second, we're going to talk about what we're going to do basically in the next season. And just a quick note for anyone getting into engineering, etc. Adam Savage put it in its best words: the difference between science and screwing around is writing it down. So this is my print count, and I wrote down all the small details I changed, which led me to this run. You saw the numbers, but I filmed this beforehand, and this actual Benchy was done with 0 on the pressure advance side. It was going up 215 degrees. I added the priming element, and we're running 480k accelerations at 2 amps per motor. What an epic journey this has been. You followed me on this is the 10th episode of the Minuteman project. I had no idea where this is going, but I'm so glad I did it and just started this project. And what we achieved today is basically tying the world record. And I got a huge respect for Monica McWoof, which is doing all of that on a modified Ender 3. And I got huge respect for all the other guys participating in this really, really hard challenge. I want to give you a cliffhanger to maybe a season 2. I will be on vacation during January, but after that you can expect some pretty wild things here. So in the first episode, we identified 3 main reasons why we can't print faster. The first being extrusion. With what we've seen today, I've been running this at 210 degrees and extruding 150 cubes of material. I have to do a lot more research into doing pressure advance. Maybe in a future version we have to update this channel inside, but the system itself is working. And we got loads and loads of headroom. I think the 1 minute Benchy is in that thing. Maybe we have to change a few things up here. These Bondtech extruders are freaking great, but maybe we should get rid of that gearing so we won't run into backlash issues, etc. But this is just a maybe. Okay, moving on. Second part is cooling. And what we got over here is like the prototype for the updated cooling situation. So this is one of those piezo vaporizers. And what I basically want to do is enrich the stream of cooling air with some kind of a different fluid. In this case, it will be a mixture of water and glycerine. That's at least my proposal for now. And the first results I got with this kind of setup are pretty interesting. I put a very short video up here on the screen. Also, I'm planning tests with dry ice, liquid nitrogen, and all that goodies. Let's see how far we can push our cooling capabilities. Well, yeah, and last but not least, this is our current, this is an older type, but you get the idea. We're moving around like 90 grams of material with our current setup of air bearing. And I've been catting around left and right, and while I think the air bearing is a very neat solution for what we're doing here, if we want to run a sub 1 minute run with open loop steppers, we have to change things. So my next iteration of the bed will be something like this. And it will be powered by way smaller Dyneema cords. And also I've got a very special package here. This is been requested by many people, and I actually talked to Omranello by Devil Design, and he sent me those kind of maniac NEMA 17 motors. And while the nanotech motors are doing an absolute great job for their application of the weight and inertia matching is wonderful. I didn't have a single skipped step today. I'm running just at 2 amps, but I think for this kind of a setup, a lower inertia motor is better. And according to their spec sheets, these will deliver 0.8 Newton meters until they reach very high frequencies. So I'm really pumped on how these work out. They even got a thermistor built in. I've got a lot of stuff planned to eventually. I'm not gonna promise anything. It is still the question, is a sub 1 minute even possible? Like, I've ran 500k accelerations today, and I can really push it with everything I got in terms of cooling the motors and putting all the amps I got, and I maybe can reach 1.2 million. But still, this is good for like 1 minute 30. So we have to go a lot higher than that, and all the other issues like extruding and cooling have to be way up there. With that in mind, I hope you enjoyed this special episode. It was a pleasure having you guys here. I'm really pumped on the result. Again, a huge thank you to PCBWay for sponsoring this episode and sending me all those needed upgrades for the machine. Those held up perfectly. And yeah, I'm really looking forward to sending them another cat drawing for my future videos. Have a nice Christmas time. See you again in 2025. Bye.
Powered by motors from Nanotech, celebrated for the hypersynchronous torque complicated machinery, as well as video intros, knows no bounds. Torque realignment. Phenomenal. A girdle reluctant cables. These are anchored on a granite foundation to prevent anything resembling instability. Rated for the hypersynchronous torque realignment. Equilibrium engineering. Gravitonic equilibrium engineering. Gravitonic equilibrium engineering. Okay. Of course,